can do it for her. Okay, back to my talk. I'll just remind the title again: Energy Harvesting and Cell Zooming in Heterogeneous. We will have lots of fun today.
I come to marry willfully in Paru.
Can go back to that one. Yeah. Okay. About this topic, I will first give you some motivation toward this topic, and then I will say a few words about research methodology which I use during my research. After that, I will define what's cell zooming and what's the concept behind it. We will see two different scenarios: a simple one, which is single-tier PVT network, and the other one is K-tier HetNet with energy harvesting. My presentation will be concluded by a summary and conclusion again. So the next generation of mobile communication will come to overcome a lot of challenges, like very high data rate, low latency communication, ubiquitous coverage, and at the same time, it aims to address energy issues from both economic and environmental point of view. To give you a sense about how much energy is consumed in telecommunication industry, I can say just in Italy, communication operators use up to 1% of total power consumption nationwide. In this graph, you can see the increasing rate of carbon footprint in the communication industry. It will exceed 300 megaton per year in 2020. And what we will have in 5G is millions of connected devices through device-to-device and machine-to-machine communication. All this communication link, wireless link, have transmitter and receiver which use energy and, of course, produce CO2. Just keep it in mind that in a wireless network, more than 60% of total power consumption consumed in base stations. So it's more important to focus on base station rather than just focusing on transmission rate or transmission power. And when I'm talking about energy consumption, I'm talking about money, because we have to pay for energy that we consume. To address all these challenges, some paradigms have been suggested, something like random cellular networks, multi-tier HetNets, MIMO, massive MIMO, millimeter wave, and so on. In this work, I focus on the first type, which means multi-tier HetNets or a random cellular network. During my research, I used two mathematical tools, stochastic geometry and MARKOV model. In the stochastic geometry, I use this tool to model heterogeneous cellular networks in which both mobile users and base stations are randomly located. And commonly used process model in this area of research is Poisson point process, which I also consider PPP in this work as well. And the Markov chain has been used to represent network transition between available and unavailable channels in the network. You know, to initiate a successful call, we should consider several parameters like call arrival rate and so on, duration of call and everything. These are the parameters which are captured during this Markov model. I bring a Markov diagram here. You can suppose that we have a network state of pair of M and N. M shows the number of occupied channels, and N represents the number of available channels. And C is a total, the maximum number of available channels. Some channels might not be available because of the channel quality, like low SNR or something. So using this Markov diagram, we will reach to a steady state probability of pK. And to find blocking probability, we use this diagram, and you know that when one arrival call would be blocked if we don't have any free channel for that. It means that number of occupied channel is equal to total number of channel that we have. So we can just using this steady state probability to find that blocking probability. Okay, back to main topic of this presentation. What is cell zooming? The concept of cell zooming comes from the idea of changing base station coverage area, probably dynamically based on the network traffic load. You know, in conventional network planning phase, base stations are planned based on fixed range, which is imposed by maximum transmission power that we have. But you better know that a traffic load fluctuates in both temporal and spatial domain. And the other way which cell zooming can be implemented is is turning off some base station and offload their traffic to a neighboring cell. And you know that when we have low traffic on some base station, maybe it makes sense, or it gives us efficiency when we offload their traffic to neighboring base station. The basic approach towards cell zooming is shrink the coverage area of some cells, zoom in, or expand some others, zoom out, or do both at the same time, zooming and zoom out. Or as you can see in right-hand side figure, turning off some base station and use the other base station to just compensate this coverage hole. Previous work showed that in some specific scenarios, cell zooming can achieve about 20%, or even in some specific areas, or 50% of power saving using just these methods. And also this can use for sector-based network. In our first system model, we consider single-tier Poisson-Voronoi tessellation PBT random cellular networks, and use each of these cell zooming techniques. The first one is telescopic one, which means adjusting coverage area of base station. Coverage area here shows with RC the radius of the coverage circle of each base station. And the other cell zooming technique is on-off scenario, which we model this scenario using thinning process. To achieve the first cell zooming technique, we can either choose the cell radius or transmission power through one of these two sets. And to model the other cell zooming techniques, we just reduce the density of the base stations. For a first system model, we just independently turn off some base station using this row, which is called retention probability, the probability that one base station stay on independent of other base station. Of course, this row can be more complicated function as a function of neighboring base station or other function. The SINR in this scenario is, I think, quite well known for all of you.
So the D is somehow related to Pmax, or?
Yes, exactly. Yeah, D is the maximum coverage area, coverage radius, which comes from using this Pmax, maximum power consumption of each base station.
Okay. So you will never, like it is not guaranteed that you will always have a circular coverage region, right?
Yeah, we assume that we always have circular coverage.
Okay, that's the assumption of circular.
Mm-hmm. Yeah.
So,
Please.
so the base station, how does it select which power, transmission power to use from this set?
Actually, we say that for this scenario, but it can choose by itself. You know, in a distributed algorithm can be used to find the transmission power or its radius based on traffic load which they have, or maybe available energy which Yeah, yeah. For example, we will see in energy harvesting part, we have some energy constraint due to energy harvesting scenario. So that constraint imposes us to choose this radius or even this retention probability. In this single tier network, we found ergodic capacity per user for our system model. Then we found areal spectral efficiency and energy efficiency in this case. And to find energy efficiency, we consider both constant power consumption and transmitted related power consumption. And I told you that more than 60% of total power consumption in wireless networks using base station. So it's important to also consider this constant power consumption, which comes from cooling or other stuff in base station into our energy efficiency computation.
So, in the definition of the energy efficiency, there are some parameters. L, what's
L is the number of users that we are serving in one base station. C is capacity per user, bandwidth, yeah.
So I'll find the power amplifier efficiency.
It's actually captured in PC. The power
amplifier efficiency, that's captured in PC?
Yeah.
Okay. So
Yeah, PC is composed of several components, which is
alpha is then this partial section.
yeah. In this graph, I don't know why it's like that. You can see areal spectral efficiency and energy efficiency based on cell radius. In this case, we use the first cell zooming approach when we expand or shrink the cell radius of base station. And you can see that expanding cell radius does not always mean that we have more energy efficiency. And as long as we have enough resource to serve users, the more user we have, the higher energy efficiency and areal spectral efficiency that we got. You also can see that there is an optimum cell radius which gives us higher energy efficiency in this work. Also, in terms of changing the density of the base station, you can see that there's also optimum value of transmission power, and also as long as we have enough resource to serve all the users, the lower base station that we have, of course, give us better energy efficiency. And in right hand side figure, you can see the trade-off between energy efficiency and areal spectral efficiency. The interesting part of this figure is that it gives us a working region. Right-hand side of this figure is our working region. It doesn't make sense to, for example, find a point in left-hand side because we always have a better energy efficiency or better areal spectral efficiency with the same other efficiency that we need. In a K-tier network, we just assume that all the base station only is powered by energy harvesting, and all of them are equipped with finite size batteries. So it brings some challenges to our system. Means that because of the random process which we consider for energy arrival to these harvesting modules, some base station might have not enough energy to serve user, so they have to be turned off. And we consider a K-tier network. Each tier is independent Poisson point process. And again, we consider two cell zooming techniques. This time at the same time, we apply both techniques. Telescopic one, which we apply this model using a cell zooming factor, BK, and also on-off scheme, which this time imposed by energy constraint. For example, the base station, which doesn't have enough energy to run, have to turn off. We found this per tier association probability means a typical user associate to each tier of the base station based on this probability. And we also found ROCA, which is retention probability. Also, you can see ROCA here in this equation too. Actually, ROCA imposes us the density of active base station. Coverage probability has been derived in this scenario. And the more important one is this retention probability. We can find retention probability in each retention probability of the network using the battery size of each base station, the energy arrival rate, and the necessary and sufficient condition to, which enables us to solve this equation is a conservation energy equation. Means that total energy that we harvest from environment can not be less than what we are using in our communication system. After finding this retention probability, which gives us a final active density of active base station, we found cell throughput and special spectral efficiency of the network. And you can see again here that in energy efficiency formulation, we consider both transmission power and non-transmission related power, which is a summation of energy which is used during manufacturing of the base station and also the maintenance of base station, which both consumes energy, and this amount is, let's say, huge amount of energy which need to be considered in our study. So, interesting figure. In these two figures, we just compare the coverage probability and blocking probability of three-tier network. The first one is our proposed model, energy harvesting cell zooming network, and the other one is a regularly used in literature, non-energy harvesting unbiased network. You can see that although we are not sure about energy arrival and available energy to run the network, but we achieve higher probability both in coverage and blocking probability, which gives us good result in this case. In terms of special spectral efficiency and also energy efficiency in this scenario, again, our proposed model, which use both energy harvesting and this cell zooming factor, means expanding or shrinking the coverage area of a base station, gives us a higher spectral efficiency and energy efficiency compared to non-energy harvesting unbiased network. So, almost the last slide. I have introduced cell zooming as a viable approach toward green communication. We investigate energy efficiency and spectral efficiency using stochastic geometry in green communication, and proposed a new expression for ergodic capacity in a single tier scenario. Trade-off between aerial spectral efficiency and energy efficiency have been shown, and the performance comparison between our proposed model and a commonly used model in the literature proposed. We show that in both cases, our proposed network have better performance in terms of coverage and blocking probability, energy, and spectral efficiency. Thanks for being here, and if you like to have more detail about this work, you can easily go to the paper which is cited here. Thanks again, and I would be more than happy if you have any question, and I can answer that.